Have you ever wondered why the Pacific and Atlantic Oceans don't mix extensively? A fascinating question, isn't it? The answer lies in the intriguing world of water density. Water density, a measure of how much stuff or mass is packed into a given volume, is not constant. It fluctuates, influenced by factors like temperature and salinity. Now, imagine a glass of water. If we chill this water, the molecules slow down and come closer together, making it denser. On the other hand, if we add salt, the water molecules have to make room for the salt particles, increasing the water's density. So when we talk about the oceans, we're dealing with vast bodies of water that can be both cold and salty. As a result, these waters are denser than their warmer, fresher counterparts. Take the cold, briny depths of the North Atlantic, for example. Here, the water is so dense that it sinks, forming a deep current that flows all the way to the Southern Ocean. This cold, salty water doesn't readily mix with the warmer, less salty waters of, say, the tropical Pacific. But it's not just about cold and salt. The density of water also changes with pressure. The deeper you go, the greater the pressure, and the denser the water. This adds another layer of complexity to the mix, or rather, the lack of it between our two oceans. The interplay of temperature, salinity, and pressure creates layers or strata of water with different densities in the ocean. These layers act like invisible walls, creating barriers that hinder the mixing of water from different regions. This stratification, this layering based on density, is a key reason why the waters of the Pacific and Atlantic Oceans maintain their distinct identities, despite being part of the same vast global ocean. So the density of water plays a significant role in keeping these two vast oceans from mixing extensively. But that's just the tip of the iceberg. There are more factors at play, and we'll dive deeper into those in the next scenes. Stay tuned. Now consider the temperature differences between these two oceans. The Pacific and Atlantic Oceans, while both vast bodies of water, are subjected to different temperature ranges. This is largely due to variations in climate, ocean currents, and geographical locations. Climate plays a significant role. The Pacific Ocean, spanning from the Arctic to the Antarctic, is influenced by a broad range of climates. It experiences frigid polar chills in the north and south, and tropical heat near the equator. The Atlantic, while also stretching from the Arctic to the Antarctic, is generally warmer due to the Gulf Stream, a powerful warm ocean current originating from the Gulf of Mexico. Ocean currents too contribute to these temperature differences. The Pacific's Humboldt Current, also known as the Peru Current, is a cold current that cools the waters of the eastern Pacific. In contrast, the Atlantic's aforementioned Gulf Stream warms the eastern coast of North America and the western parts of Europe. Geographical locations of these oceans also play a part. The Pacific, the world's largest ocean, has a greater surface area exposed to the cooling effect of space, which helps to keep its overall temperature down. The Atlantic, on the other hand, is narrower and more influenced by the warmer land masses that surround it. These temperature differences result in the Pacific tending to have cooler waters in many regions compared to the Atlantic. This difference in temperature contributes to their different densities, with cooler water being denser than warmer water. And why does this matter? Well, just as oil and water don't mix due to their different densities, the cooler, denser waters of the Pacific and the warmer, less dense waters of the Atlantic also don't mix extensively. Instead, they tend to stay within their own boundaries, maintaining their distinct characteristics. These temperature variations further enhance the segregation of the Pacific and Atlantic Oceans. So, the next time you gaze out at these majestic bodies of water, remember that beneath the surface, there's an intricate dance of temperatures at play, contributing to the marvel that is our world's oceans. Apart from temperature, salinity also plays a crucial role. Now let's delve into the concept of salinity, which refers to the concentration of salt in water. The Pacific and Atlantic Oceans, while both vast bodies of salt water, don't have identical salinity levels. This discrepancy is due to factors such as precipitation, evaporation, and freshwater input from rivers. Consider this. When there's heavy rainfall, it dilutes the salt concentration, reducing the salinity. On the other hand, In regions with high evaporation rates, water molecules escape into the atmosphere, leaving behind salt, and thus increasing the salinity. Additionally, fresh water from rivers flowing into the oceans also alters the salinity. Fresh water, being less salty, dilutes the ocean water, again, decreasing the salinity. These variations in salinity impact the density and consequently the movement of water, leading to stratification. This means that water with different salinity levels tends not to mix freely, creating distinct layers within the ocean. So differences in salinity also contribute to the limited mixing of these two oceans. The circulation patterns of the oceans are another key factor. Each of the world's oceans, including the Pacific and Atlantic, has its own unique circulation system. These patterns are not random, but instead are driven by three main factors: wind, temperature gradients, and the rotation of the Earth. Let's start with the wind. Wind blowing across the surface of the ocean pushes the water, creating currents. These currents don't just flow on the surface, but also extend deep into the ocean, carrying water across vast distances. The wind's influence, however, is not the sole driver of water circulation. Temperature gradients also play a significant role. Water at different temperatures has different densities, with colder water being denser than warmer water. This difference in density causes water to move, with denser water sinking and less dense water rising. This movement, known as thermohaline circulation, creates a global conveyor belt of ocean currents that carries water from the tropics to the poles and back again. Now, the third driving force behind ocean circulation is the rotation of the Earth, a phenomenon known as the Coriolis effect. As the Earth spins, it causes moving fluid like ocean water to follow a curved path rather than a straight line. In the northern hemisphere, this makes currents veer to the right, while in the southern hemisphere, they veer to the left. These three factors combined, wind, temperature gradients, and Earth's rotation, create the circulation patterns we see in the oceans. These patterns include the currents that flow like underwater rivers and gyres, which are large systems of rotating ocean currents. In the case of the Pacific and Atlantic Oceans, these circulation patterns help maintain their separation. The currents and gyres confine water masses to their respective regions, creating a boundary between the two oceans. In essence, the water from the Pacific and Atlantic Oceans is kept largely separate by their own circulatory systems, each with its distinct characteristics. These unique circulation patterns confine water masses to their respective regions, limiting the mixing between the oceans. Lastly, let's talk about the natural barriers and limited mixing zones. Our planet's oceans are not just vast bodies of water. They're complex systems shaped by a myriad of geographical features. Underwater ridges, continental shelves, and vast land masses all play a part in influencing ocean currents. These natural barriers act like walls, guiding the flow of water and preventing extensive mixing between the Pacific and Atlantic Oceans. Let's dive a bit deeper. Picture an underwater ridge, a mountain range hidden beneath the ocean's surface. These ridges rise from the ocean floor, influencing the path of ocean currents and creating boundaries that restrict the movement of water masses. Similarly, continental shelves, the extended perimeters of each continent, create natural divisions between different bodies of water, further maintaining the unique characteristics of each ocean. Next, consider the influence of land masses. Continents and islands act as colossal partitions dividing the world's oceans. They not only dictate the course of the ocean currents, but also contribute to the distinct identity of each ocean, maintaining the unique temperature and salinity profiles that we discussed earlier. Now, while these geographical features play a significant role in limiting the mixing of the Pacific and Atlantic Oceans, it's important to note that there are areas where these mighty bodies of water do meet. A prime example is the Drake Passage, the body of water between South America's Cape Horn and the South Shetland Islands of Antarctica. Here, waters from the Pacific and Atlantic Oceans converge. But don't be mistaken, the meeting of these waters does not result in a grand fusion. Instead, the mixing is often limited and localized. Why? Well, the factors that we've been discussing all along still apply. The waters from each ocean have their unique densities, temperatures, and salinity levels. These differences, along with the influence of specific circulation patterns, limit the extent to which the waters can mix. Instead of blending into a uniform mass, the waters tend to maintain their distinct properties, leading to a fascinating phenomenon where the two bodies of water meet but don't mix extensively. So, there you have it. The Pacific and Atlantic Oceans, each with their unique characteristics, influenced by a host of geographical, climatic, and physical factors, may meet at certain points on this beautiful planet of ours, but they largely remain separate entities. In conclusion, while there are areas where waters from the Pacific and Atlantic Oceans meet, the combination of water density, temperature, salinity, circulation patterns, and geographical features limit the extent of their mixing.